So hi, everybody. My name is Dave McAllister. I work as a technical evangelist in what's known as the App Dev division for Splunk. And I'm going to be covering a couple of things during the day. But very honestly, Splunk has this belief that everything really starts with each person being a million points of data. So I thought I'd share a couple of points from my side. One, I'm owned by 3 cats. I am completely used to being ignored at any moment. 2, I spent 10 years as a soccer ref, so I'm used to people disagreeing with me at least 50% of the time. And 3, I'm married, so I have a witness that I do not read minds. Feel free to ask me your questions, hopefully in the Slack channel, and I will promise to get back to them. So the first things that I want to talk about is sort of how the world has changed. And we've seen this move from a tightly coupled application, and we've seen this in talks earlier today, where we're moving to this loosely coupled entire environment of cloud-first microservices and serverless architectures. These pieces give us some additional functionality here. One, while we have found things are easier to build because we're not responsible for each individual piece, the complexity has continued to mount. As part of that, we needed to move into this thing called observability. But very honestly, observability starts with something. My favorite quote, Sir Arthur Conan Doyle, of course, Sherlock Holmes, the scandal of Bohemia, you see, but you do not observe. And observability is not just looking across the surface. Observability requires that you deal with a deep dive to find out what's going on underneath of it. Therefore, we need to be able to see all of the dimensions that make up an observability platform. We need to be able to understand and drill into that environment at any given moment. And observability in this case is honestly a filter problem. It's a signal to noise problem. But the problem is that it can't be treated as a signal to noise problem. It's a signals, not noise problem. Generally speaking, when you're bringing in additional data that you're looking at noise, there are 2 basic ways that you can approach this problem. One is by doing a bandpass filter, filtering only the things that you think are important into your final environment. The problem with this is that you start immediately eliminating outliers, things that are actually probably the most important data when you're drilling into the underlying complexity of your system. So you cannot get rid of data. And in fact, in general, our tool, I've heard others talk about this as well, don't get rid of data. Data is useful. No matter what, your data is going to be useful inside of here. And so that leads us to the second approach, which is to figure out ways that you can make the data useful, even with all of its additional complexity and cardinality inside of here. So those become really important items when you're looking at this overall observability process. Now, everyone actually does have their sort of own version of what makes up observability. And observability, the TLDR version, it's the quality of your software. It's the quality of the service that lets you understand how the systems are behaving. What that means is that you have to design a system or make the system observable for this. It's also, in engineering purposes, defining the exposure of those variables in a manner that allows you to infer its behavior. Similar, you can think of this in a sense, the shipping of concrete was a wonderful example. But if your light goes on in your car and your car suddenly says that it's running hot, you now have a piece of data, but you do not know what's happening underneath that. You need to be able to drill into deeper data sources to figure out whether your oil has gone dry or your water pump is not working or your sensor system has decided that it's going to list as hot when it's not. So you've got to be able to drill into it and find more and more information as we go forward. The other thing is that observability is not one-dimensional. It is not to just looking at one piece. It's looking at all of the pieces here. You know, it should consist of your logs. It should consist of monitoring. It can consist of events and tracing. It can consist of anything else that you care to think about. We had a problem once where we were working one of our customer base, and we had one customer that was having problems, and he had a slowdown. This is across 1,500 cores. Nothing else was showing bad. The numbers weren't showing bad. And we actually ended up drilling all the way down into the thread level to figure out that there were two causes inside of here. One, somebody had misconfigured the system, so it was no longer doing elastic balancing. Two, they had shifted the way they sent us data from large blocks fairly seldom to an amazingly huge number of small blocks of data. And what had happened was the two things together worked to cause our problem. This gives you an indication that you've got to be able to cross the boundaries. It's not just the apps, not just the services, it's also the disciplines. So you need to be able to cross those boundaries going between operations to development. You also need to be able to cross those boundaries into business things inside of this. And last, anything that slows you down is bad. We live in an instant gratification society. And so therefore, things that slow down are not acceptable to the customers. So you probably have seen the three primary pillars of observability here: metrics, traces, and logs. Metrics are real simple. Do I have a problem? This is how you figure out what's going on. Prior to this, the concept has always been metrics show me things I know could go wrong. When we get into observability, they start showing us things that we didn't even think could go wrong, that may be going wrong for unknown reasons. Traces help us indicate where the problem is. And there have been some great talks earlier today that talk about how to use traces to determine the timing structures of here. And traces do heavily get used on a duration basis here. And then finally, logs are the drill-ins that let us look at exactly what this application or system or service was doing at the moment that caused the problem to occur. Keep in mind, an error doesn't have to be a failure, and we'll cover a little bit more about this, but these three things work together to give us the deep dive, the dimensional capability to figure out what's happening across the entire model. So shorthand, everything's an event, but events only exist if they're recorded or measured, or the standard saying, if a tree falls in the forest, it make a sound. If you don't recover it, if you don't measure it, and you don't keep it, it didn't happen. And so each of these pieces has its own aspects of things that we need to keep in mind for this. Metrics are compact, they're efficient, they're blindingly fast. They may not be sufficient to solve the underlying causes. They may not actually be complete. Depends on how you're bringing your metrics in across this. Logs are full fidelity, but they're relatively bulky at full capture. Also, logs are dependent on the person that's decided what information to give you within that log. Former colleague of mine thought it was very clever to write all of his logs outputs in Russian. After we figured out, the first time something went wrong, we had to look at his log files. We had him go back in and do the translations because that's not very useful for the vast majority of the people at my company. So, and then traces are cool. They're the new hot thing here, but they require work. They require instrumentation to establish. And there are easy ways of doing that, and there are hard ways of doing that. Logs can be bulky. Traces, because you're actually capturing a tremendous number. The current average is that for a single e-commerce request going through a system, there's somewhere between 5 to 10 span information captured for each request on each step. So you can see that traces can all of a sudden become very bulky as well. So just a quick thing. This is kind of a picture of what a microservices architecture looks like to the outside world. My hat tip to Martin Fowler for this. This is Amazon CO UK's ordering page. And the inside of this, you can see a number of services that are happening going across this. And behind each of these services are other services. So for instance, you have an inventory service that's actually calling into a database and maybe looking at its locality. So there's a number of pieces that happen going across all of those other things. So this becomes a very complex model. So primarily, it's a distributed system with a distributed development model. And this is where life gets interesting, crossing the boundaries of what we need to monitor and what we need to drill into. Likewise, a lot of this is driven through Kubernetes. Kubernetes is massively in use. It is the top container orchestrator in the world, but it also adds some unique challenges to this. Things are not always there. Containers spin up and down in seconds. You actually don't know where Kubernetes is going to put something. You ask it to put it on something that matches your needs here. And again, if you're not recording it and not capturing it, it may not exist. So a pod failure, if you did not take the steps to capture the data around what was going on in the pod, is gone. And so you may not be able to actually recreate the ability to find out what went wrong with your pod unless you are capturing that piece of information and that data source that's happening inside of this. So Kubernetes makes life a lot simpler, but it does not make life less complicated at the same point in time. And just because I'm fairly passionate about this, observability is not an end goal. It should be a loop. So the duality of observability is controllability, the ability to control what's happening inside of here. And telemetry is the method by which we get that inputs here. So a process, an app, an infrastructure uses telemetry to send us signals. Our observability is to take those signals and figure out what they meant and how they do that. The controllability aspect is where we need to close this loop. And the loop can be either an open loop or a closed loop. In machine terms, this is either computer process control as a closed loop, or SCADA, supervisory control and data acquisition, as an open loop. In our space, in this world of software and applications and infrastructure, that equates to, does it send me an alert and help me understand what I need to change to make my application perform correctly? Or is it automated? For instance, rolling out a new version of a microservice, since microservices quite often aren't rolled out all at the same time. You roll out a service when it's ready. All of a sudden, did I see a huge number of errors spike inside of here? The system could take the activity to automatically roll back to the last known stable state, while also alerting the operations and the developers that there is a problem that needs to be researched onto what the application piece closed. So observability really needs to stop moving from this see something, say something, to see something and do something. So what is RED? RED's pretty easy. It's a spinoff of Google's Golden Signals. It was definitely SRE related. It's in their SRE handbook. And it was originally mentioned by Tom Wilkie, who was at Weaveworks at the time. It's made up of rate, error, and duration. And it was designed with this concept of request-driven systems for microservices. Interestingly enough, you can drop off the word microservices. RED works really well with any request-driven system. It doesn't necessarily work well with batch type of operations, though there are exceptions. Batch, for instance, being used in a serverless environment, it works incredibly well in that space here. But it really was designed for this request-driven model. And what it does is it breaks down and lets us know how each of our services is working. And this gives us the ability to look deep inside of a system, not just at the overall, the final product, but actually each of the pieces and how it's basically contributing to what we're seeing in the final product base. So when we move into this, what we find very quickly is that complexity matters. And so we need to be able to deal with that complexity. There's lots of interrelationships. We have this services-based environment that can spread, can be elastic, can manage back and forth here. And at the same point in time, we have things that are no longer there or no longer where we last saw that they were. So we need to be able to do simplicity and abstraction to resolve this clutter. Again, we have lots of signals coming in here. How do we simplify it without losing the important information? And that's why we need to be able to retain this complexity aspects for looking at the gotchas and the ahas that happen inside of here. We need more than just being able to look at overall systems. We need to be able to drill down and look at any specific functionality and piece as it occurs. And while you often hear that observability is not monitoring, it starts with monitoring. And I like to call it monitoring at the Chuck Norris level, because it, as we all know from Chuck Norris's shows and movies, Chuck Norris always took action. He didn't just see something happen for this. Rate, error, and duration, in a sense, can break down into metrics, logs, and traces. But it provides us another level which says, how do we recognize the issue and how do we recognize the root causes. And so those pieces together give us this unique capability of seeing across all the platforms, all the levels, as well as all the underlying infrastructure. So rate's pretty easy. Number and size of requests on a network system. It can be anything that's transmitting data. It can be middleware, it can be Kafka, it can be REST, it could be API calls. It could be the output of service messages like Istio or Linkerd inside of here. Any environment that can fail on peak traffic is a target for rate monitoring. And interestingly enough, the inverse is also true. Any environment that can fail on minimal traffic is also a target for rate monitoring. So imagine, for instance, Amazon Prime Day, and they see no requests going through the system. So the request rate is really low. There's no problem there, but there's definitely a problem somewhere in the system. So errors, we've all dealt with errors. Errors are problems that are incomplete, incorrect, or unexpected. And they can be code failures. They can be production load bugs. They can be communications issues. They can be peak loads. And the corollary there is that testing for production is not the same as running in production here. Errors require incredibly rapid response. They also usually require very point-specific response. And so you need the ability to do this deep dive, high fidelity, and you need it as soon as possible. A Google study in, I think, 2017 showed that you would lose well over, or actually you lose everybody if they wait 5 seconds for their shopping cart on their cell phone. And so think about that. Somebody's not willing to wait for their shopping cart to appear for 5 seconds, they will leave you. And at 10 seconds, they will go on social media to complain about you. So we need to be able to resolve these things as fast as possible. So errors start creeping into that picture. Duration is all about time. And we've heard a lot about the world that duration lives in, distributed request tracing here. And really, its entire job is, what order did things happen in? How long did things take? So we start being able to answer things. How do I know it's slow? And then what took so long? Which piece was long inside of here? And it can be a service. It could be a communication path platform. Both the client side and the server side are important. Client side might be a little more important. And I'll show that in a little bit here. But basically, when you look at this with distributed request tracing, there are lots of closed environments here. But here, you really want to make sure that you're using an open product. Open telemetry is near and dear to my heart. One of my coworkers did a workshop on open telemetry earlier today. But if you're using open tracing, you're using open census, but you want it to be open because you do not want to have that proprietary piece that drops in. So with that, let me do a real quick. So this is showing off a little bit of a red environment. And this is a standard dashboard for a microservices-based environment. And what I'm looking at here is, honestly, rate, errors, and duration. And I can actually break it down by looking at this as a number, or I can look at it as a timeline strip. So I can start looking at sort of trending lines. Humans are still better at extrapolation of trend lines than computers. Computers are getting better, but they're not quite there yet. But you can, for instance, see that I have an error rate that's pretty abnormal for this. And so I would expect that there's something going on. From this, I can, for instance, step in and start troubleshooting. What this is doing is giving me the ability to start drilling into the dimensional aspects as quick as possible. And I notice there's a peak right about here. So I'm going to load up traces. So these are some example traces that come into this. But when you're looking at traces, this is pretty traditional trace data that's happening here. This is a standard waterfall plot. And you can see each of the pieces going across this. You can also see the span performance broken down by how things are spanning, how the distributions are. You can also start looking at how this is applying across your entire system. So it's not just looking at what's happening inside of that request, it's actually looking more at what's happening across your system through this. So for instance, my HTTP request is taking about 46% of my external. my various services that are taking up the application piece, and the rest of them are network traffic. And so this starts giving me instant sets of information about what's happening inside of that. However, you should not have to just look at examples. And this takes a while because I have a huge number of traces, but you can actually should be able to go look at every single trace that you have. You should not be limited by the amount of data that someone else picked for you. You should be looking at the data that you think is possible and you think is important. So sampling is not a good concept. And when you're looking at a red environment or a microservices environment, sampling is not useful inside of that. And of course, you always need to be able to see what's happening. This is a fairly simple little checkout example for this, but you can start getting more and more information just by looking at what the functionality in between these things are. And continue on that way. You can also do little things because you can, again, look deeper into this and start crossing over. I can, for instance, very quickly see that I have a node that's showing a root cause error. Root cause in a tracing environment is the lowest instrumented service to which is reported an error for this. And I can step directly into my infrastructure, quickly find out what's going on with that service. I notice down here, this is a demo, and then I've got something that's eating a lot of memory. So I can click into that and find out, again, that I probably have a configuration error in one hand, but I also probably have an application error because something is using a whole lot of memory inside of that. And so that's a very quick way of pulling all those pieces together, but it starts with that red concept. It starts with the ability to recognize and look at that. So why red? Well, it's really easy to remember red. Most of y'all will be able to walk out of this and be able to tell me what red means. Hopefully it'll stick with you. Interesting enough, one of the things that we found is that it reduces decision fatigue. We have lots of services groups, lots of microservices groups. They don't all work as one group. They work on clusters of services here. And when we started talking about how we were going to monitor those services, there was a lot of debate about, oh, well, I need to be able to see this. Oh, I need to be able to see that. Red gave us a common starting point. It let us have a consistency across all these groups while giving the ability for those groups to also customize it to their own unique needs. But Red gave us that as a starting point. And that made it really simple for us to get up and running to look at this monitoring capability. It also helped a lot with our automation. We now know what the data is telling us. We have a common set of definitions for what it means when something happens for this. And finally, it's an interesting proxy for user happiness. If I can look at it, request, and tell you how long the requests are taking going through my system, I can give you a pretty good indication that it's matching pretty well to what the user's expectations are. So it's not always the great news. The problem with Red is that it can interact in unique ways for this. And so you can get a rate problem that's actually being caused by an error or by a slow consumer. So you can have something that's working perfectly fine, but showing up as a rate error, even though the problem is nothing to do with your network or your communication pathways for this. Likewise, errors can be bandwidth mismatches, or the response time is not coming back for something is timing outside of here. And the durations can also be a no response, an error that's simply going nowhere here, or you run into a bandwidth limit in your infrastructure. And so Red has these unique interactions that you've got to worry about as well. So it's not just the infrastructure or application, it's both. But in complex environments, your tool should be able to help you out, figure out your service maps for you, figure out what you should be interested in, and help guide you without limiting you to this. If you can't drill down, don't bother. And so Red helps you through this dimensional breakdown. Earlier talked about being able to use tags. This is really important. That's your cardinality aspect that's very, very important in a Red environment. So the Zen side, from an external customer viewpoint, they really only care about sort of these three things: the request and how long it took And was it successful? From an operator viewpoint, we expand that. It's across all of them. Are the request latencies good? Are the rates good? And how is my concurrency versus my system looking, going across its components for those pieces here? But you, from an operator viewpoint, they have to drill into that singular viewpoint at any given moment. I ran a nonprofit for Stanford called Philosophy Talks, so I always throw my philosophy bit in here. Instrumentation by itself is not an answer. It'll help you find an answer. Metrics are powerful, but not solely sufficient. The ability to tag and slice and dice this matters tremendously in how your metrics are useful to you. You want to look at the work that's going on, not the service, the work. Let's see how the service looks for the workload here. And you're really not trying to deliver observability. You're trying to do mean time to detection, mean time to response, and mean time to resolve. And so, summary, observability is more than monitoring, but it starts with monitoring. And Red wins in this microservices-based applications for how we can observe the application structure and the infrastructure here, while keeping those insights that are so important for us things. You need to always keep in mind that Red itself interacts in interesting ways. And finally, find the right tool, the tool that gives you the clarity and insight that you need to solve your problems and reduce those wonderful MTTs. And with that, thanks for your time today, and I will turn it back over to you, Paul.